J'ai le plaisir d'accueillir Olivier Bournez de l'École Polytechnique pour cette nouvelle journée, ou plutôt que journée, même pas demi-journée des séminaires du pôle calcul. Et voilà, Olivier n'a pas besoin de présentation, je laisse la parole à Olivier. Et est-ce que tu arrives bien à partager tes diapos, non? Tu as toutes les autorisations qu'il faut. Donc,
Okay, I guess I should do this presentation in English, right?
Yes, you can do it in English. Yeah, sure.
Okay. Okay. I hope this is sharing my slides. You see my slide, and the sound is good. Okay. So welcome and thank you for this invitation to present some of my work or work with co-authors about continuous time models of computation. And the purpose will be to discuss how we can compute with ordinary differential equation. And first, the question is, why should we care? So maybe a warning. So this is a talk related to computations and foundations of computer science. And okay, I will mostly talk about models of computation, computability, complexity, and sometimes go to biology, bioinformatics, physics.
I'm sorry, Olivier, we cannot see your slides.
Okay, great. Sorry. So let me try to do this. Is this working like this? No. It says I'm sharing. Do you see the slides?
Yes, it works.
Okay, perfect. Except that I need to. Okay, so yes. So let's start by a simple question. Suppose I want to compute some integral. So of course, as I consider myself as a computer scientist, I mean with a computer. So of course, one approach could be to use numerical analysis methods, but another one would be to use the tool that were used in the past to compute integral. And here you have on this, I hope you see my mouse, this thing here is taken from a book and explains how you can compute an integral using a machine that was used in 1930, so in the 30s. And so the purpose of this machine is to compute some integral. So it's a mechanical machine. So you draw a curve, you have a curve like this, and you move a pen, a kind of pen, a cursor along the curve. So there's a motor moving on the axis here, and on y coordinate you move. So with you and the cursor along the function, and this thing is drawing on some output table here, table traçante in French, the integral of the curve. So it's using a mechanical process that's doing integral. If you want to compute integral, another way is to use analog electronics. So this is using some operational amplifiers, ideal one. And I'm using here what is called as the integrator schema, montage intégrateur in French, where using, so maybe at school you heard about this operational amplifier, and the output voltage here is minus, if I'm not wrong, R divided by C times the integral of the input. So here I'm drawing sinus and cosinus using the principle that using two integrations and something doing a change of change, I get the solution to the fact that the integral of the integral of sinus is minus sinus. And you got it here, plot here. Okay, and I told you about computing integrals, but I should have said which integral I want to compute. So here it was the integral of a function, but if I want to compute integral of a surface, then you can also use these tools like this one, which is a planimeter. So the purpose is that of this thing, this is a mechanical tool. is to compute integral surface using Riemann's theorem. So you move a cursor along a closed curve and you read on a cursor the value of the integral. This is a quite amazing tool, and actually I do have one in my office working. So in case you want to see one, there is one on the lower side of my video. So you move this stuff along the curve and you read on your cursor the value of the integral that is output. I'm not sure you can really read it, but it works. So all of these are tools to compute integrals. And actually, when I said that I wanted to compute an integral using a computer, I have to come back to what a computer is and come back to the very basic question for a computer scientist: what is a computer? I should also admit that here there is a difference if you are English or French according to the language, because the point is that in French we have ordinateur and calculateur are not the same word, because at some moment IBM succeeded to convince everybody that the new computer was the new generation of computers, so started to call this an ordinateur, and it was not anymore a calculator, a computer. So in English, there is no distinction between ordinateur and calculator. All of them are computer. So when we talk about computer, of course, computer includes the modern computer, so like the one I'm using to do this presentation, the laptop. It includes supercomputer, it includes servers or machines like this. Or, by the way, the highest selling single computer model of all time, according to the Guinness World Record, if you know what it is. This is this stuff that the oldest of you knows. This is Commodore 64. So you know computers could be used to do to play games, and this is one type of computer. Okay, these are quite modern computers, but if I want to go to older computer, then of course I could go to the computers that you find on the books. So sometimes it's quite strange that some of them are famous and some of them are not. So the ENIAC turns out to be a famous one, which is quoted in many historical books about computing, the history of computing. And it's sometimes claimed to be the first programmable computer, which is clearly not true for various reasons. One of the reasons is that it was not programmable, but wired. So you see here the wires. So there were no program in an ENIAC, first. And second, because it was not the first, in some sense, this one here, which is a differential analyzer, existed before and it was programmed. Okay, so computer includes the ENIAC, it includes some machines like this one proposed by Lord Kelvin, which is used to predict tides, in French, marée, c'est un prédicteur de marée. Or it includes machines like this one that was used in submarines to control the elevations of the guns. So it was an electromechanical one, or it includes very old computers like the differential analyzers that were built for the first time in the 1930s, that were purely mechanical machine, and then later on electromechanical machines, then electronic machine. Okay, and okay, I could continue my game of listing old computers or way to do computations. So I told you that some of them are quoted in the book, some of them are not. This is the differential engine from Babbage. A slide rule is a computer used to do multiplication. So I showed you a planimeter to compute integral of surface. And there is even some of the computer that we found under the sea for that during decades we were wondering what they were used for. This is the example of the Antikythera mechanism, which is, so it was quoted as an open problem about what was this computer used for. No, this is a solved problem. It was used to do some astronomical computation. Anyway, my aim here is to go to computability and complexity and discuss how these computers compare. And according to a modern classification of complexity theory, I could try to project my computers over this drawing where I'm classifying the computers according to time, whether the time is discrete, is there a clock in the machine, in the computer or not. So the time could be discrete or continuous, and also the way that the data are encoded. So from a modern complexity point of view, this is called space. So the space they use. So if I try to do a projection on this, I would put for sure all these modern tools like ENIAC, Commodore, digital circuit, laptop, server, supercomputer here, because time and space are discrete. They have a clock and they work over 0 and 1. But I would also put here some of the other machines I mentioned, some differential analyzers, planimeter, type predictor here, because there is no clock. The time is continuous. It's evolving according to some continuous dynamic. And the space is continuous in the sense that everything is encoded into continuous value. I know my classification has problems and is not perfect. So for example, I don't know where exactly I would put slide rule. So how do I measure time or space in a slide rule? I don't know. Or difference engine or so. But okay. Anyway, I would like to go to a programmable machine. So clearly some of them should be avoided. I mean, the type predictor machine for Lon Kelvin was a machine used to predict tides, but only tides using Fourier series. So if I go to machines that were not tailored to solve only one problem, so go to what Shannon called general purpose machine, maybe we would call this in modern terminology universal, but it's not universal in the sense of universal Turing machine, in the sense of universal because it could solve various problems. Okay, so let's delete the ones that are not general purpose and observe that there remain two subgroups, one with discrete and time and space, and one with continuous time and space. Okay, so if I am a mathematician, I could say that both are models by dynamical systems. One group by continuous dynamical system, if you prefer by some ordinary differential equation, y prime equal f of y, where prime means derivative, and the other group by discrete time dynamical systems. So something that says that the state at time t plus 1 is given by some function of the state of the system at time t. Okay, I'm not a mathematician, as you know, if you're a computer scientist, it's not the best way to talk about computability, and we want to say something finer and discuss computability. So for that, we go to models more reasonable from a computability point of view, and for discrete time and space machine, this is models like the Turing machine. If you go to the continuous group, you go to the mathematical model that was proposed by Claude Shannon of the GPAC, General Purpose Analog Computer, in 1941. So you know, I guess you heard at least about a Church-Turing thesis that says that all reasonable models of computations are equivalent, which is clearly true for discrete time and space models. or at least admitted. And when we try to formulate the Church-Turing thesis, and when we say reasonable, it means implicitly that some of the models are considered as being not reasonable. So some models are too general or unreasonable. So one question is, what happens for continuous time and space models? How do they compare to the machines like the discrete time and space model that you may be more familiar with, like Turing machines? And just in case, so we are talking implicitly about the Church-Turing thesis, except that there are actually many variants of the thesis. So the Church-Turing thesis is about what is effectively calculable is computable. And this is different from what is sometimes called the physical Church-Turing thesis, what can be calculated by a machine is computable by a Turing machine. And here we go to a discussion about what can be calculated by various models. Is this computable, and how does it compare to computability with Turing machine? Okay, anyway, our actual motivation is to understand how analog models, so continuous time models in particular, compare to models like Turing machines, so digital models of computation, both at the computability level, so what can you compute and what you cannot compute, and complexity, I mean the resource that you would use. So to do that, we will go to various classes of ordinary differential equations, and we use the fact that they relate to various models of machines like differential analyzers. Okay, so just a few words about the model I will mostly focus on, which are this differential analyzer model. So I showed you one using pictures, but just to say that I will not really talk about differential analyzer, but show you one. But what I'm going to use is the abstraction from Claude Shannon of these machines. So the GPAC, General Purpose Analog Computer, is a mathematical abstraction due to Claude Shannon of the differential analyzers. Differential analyzers were mechanical machines of the time of Shannon. And what you must remember is that these models, the GPAC, at the end corresponds to polynomial ordinary differential equation. I mean, you have y prime equal a polynomial in the variable t and y, where y is possibly a vector. So it's a vectorial polynomial ordinary differential equation, where each of the component is a polynomial. And of course, you fix some initial condition. So this is the GPAC, and the GPAC is a model, mathematical abstraction of machine that existed. You have here a picture of the first, not the first, but the second that was built historically. So the first was built in 1931 at the MIT. It was purely mechanical. The one that you see here is 1938 version. So it's purely mechanical machine. It's working over continuous quantities which are encoded using angles. And there is no screen, no keyboard, and so on. The output is given on these output tables here, table traçante. And the first one was built under the supervision, and this one of Vannevar Bush, who is the person sitting here. And just to understand the story, so I could talk during hours about these historical points, but Vannevar Bush is the PhD advisor of Claude Shannon. Claude Shannon was an operator on this machine to fund his studies. And this is how he came to propose this model. So this electronic So these were purely mechanical, and differential analyzers were used until the 70s. Starting from the 40s, they started to be electromechanical, then purely electronic. And until very recently, we could meet people that really program this machine. This is not anymore the case, but anyway. So the most tricky part in this machine is what you see here. If you have good view, this disk here, these are integrators. So it's quite surprising that you can do that mechanically, but yes. So this is something that takes some input, so encoded as an angle, and that output here some angle, which is the integral of the input. So it's realizing an integration. And here you have one made in Meccano, so there is a very long story. In case you want to try a differential analyzer, you can still buy one. I do have one in my office, and actually one is working while I'm talking here. So if the god of webcam wants to show you on my video, you see a differential analyzer working in my office, and the output could be sent to my computer, but as I wanted to do something similar to what was done historically, I'm not sending it. So I could also send it to an output table, table traçante, but here I'm sending the output on this oscilloscope that you may see here. So it's computing something, and actually it's outputting the Lorentz attractor. Okay, so just a few words about this GPAC in short. So the idea of Shannon was to realize that basically in this differential analyzer, you have 4 types of units: constants, additions, products, and integrations. They works over continuous quantity, and constant is just multiplying the input by some constant. Summers is adding 2 inputs to get the output. Actually, this is minus the sum, but it's not so important, this minus. Sorry, did something wrong. So the product is realizing products, and the most tricky part from a mechanical point of view, but not so hard to realize using electronic, using operational amplifier, it is integration task. So you output the integral of your input, and you possibly could put some initial condition. And you say that a function is generated by a GPAC if you can build a circuit with these blocks, so that you will draw your curve on your output table, or if you prefer, for in my case, on my oscilloscope. So if I want to program with this machine, and if I want to draw sinus and cosinus on some oscilloscope, which is maybe not a surprising stuff, but as I would just say that the derivative of sinus is minus sinus. So I took 2 integrators. So if I have here x, y will be, so there is a minus in my integrator block. So will be minus the integral of cosinus. I'm using a adder with only 1 input, so it's doing a minus and another integration. So if you read that way, you are taking integrals. If you read the other way, you say that the derivative of the derivative multiplied by -1 is itself. And if you set the initial condition to 1 and 0, you will get cosinus and sinus outputted. So the program on the machine behind me is shown here. So you just program using 2 integrators. The integrators are here, they are the constants. Here you have the additions and so on. And if I do a XY drawing on my oscilloscope, I get a perfect circle, which proves that this is indeed outputting sinus and cosinus. Okay, so I could do some more amazing fact stuff like take your preferred ordinary differential equation. So one famous one, if you are mathematicians and love differential equation, is the Lorentz attractor, which is an equation of dimension 3, which was the famous example where this is a chaotic ordinary differential equation, and it was the first historically where they were observed some phenomenon of the so-called strange attractors. So you program your equation using these integrators and so on, and you get as output a curve, which is the famous shape of this Lorentz attractor, which has the shape of a butterfly. And actually, if you look behind me, you see this butterfly. I hope you see it on this oscilloscope. Okay. Okay, so clearly, you can program some polynomial ordinary differential equation using these blocks and these machines because you do have sums, addition, constants, and the way to do integration. So the way to plug the fact that the derivative should be equal to the polynomial that you would like to program. Conversely, if you have such a circuit and if you put a variable for each of the line of the circuits and write the equation and the dynamic of your circuit, you will get to a polynomial ordinary differential equation. So this is why, for me, a GPAC will be some polynomial ordinary differential equation. And okay, so this machine were used until the 70s, and just to say that you could open many programming books of that time and realize that they really look different from modern books. And actually, just to show you some intuition on why I claim and Shannon claim this model is universal. I mean, if we see such a model, we would maybe think that you are restricted to polynomial ordinary differential equation. And so if you take any ordinary differential equation, there is no reason you could plug it in the machine. But let's just do an example of programming to show you how you solve it. So suppose you want to draw the solution of this equation. I have no idea what this equation is. It's quite a random stuff that I wrote. So how do you program the machine? You realize that y prime, so the y1 prime must be the sinus of y2 to the square. So you introduce some variable y3 to be sinus of y2 and just say that the derivative of first component is the square of the third. Now, you know that the derivative of the second is y1 times cosinus of y2. So you need something for cosinus of y2. Let's call it y4. And minus this awful term. So you introduce y5. And the thing is that now you look at what is the derivative of y3. The derivative of y3 is sinus y2. So it's y2 prime times cosinus of y2. So you realize that the derivative of y2, you know it, it's here. So you just need to plug the fact that it's y4, so cosinus of y2 that you already have, times this derivative. And now you look at the derivative of y4 and see that it's minus y3 times the derivative of y2, so it should be written like this. And now you look at the derivative of y5 and see that it should be y5 times exponential of y1 plus t. So you need to introduce a new variable y6 and continue the process. So now what is the derivative of y6? It's y6 times the derivative of y1, but you know y1. And I realize at this moment that you do not need to introduce more components. So we started from some ordinary differential equations, introduce some variables, and this process ended. And actually, what we realized, historically, what engineers realized, was that for most common functions, if not all, so for all the common functions you heard at school, this process ends infinitely many steps. So the class of functions that you could generate include all common functions. Furthermore, it is stable by many operations. If you can draw f and g, you can draw f plus g, f minus g, f times g, 1 over f, of course, over the domain where f is not 0. The composition of f and g, all of them could be drawn just by writing the equation. So for example, f times f composed with g, the derivative is g prime times f prime of g, and you use exactly the previous principle to get it. And it's even stronger. If you write some ordinary differential equation, say y prime equals f of y, and f can be drawn, then the solution can be drawn. If you compile of this and you think about it, about the function you heard at school, like tangent, arctangent, sinus, exponential, and so on, all of them are obtained, could be obtained easily using the previous method, using these methods and stability properties. So this is one of the reasons why we realized that the class of generated function is very wide. And I think it may help to realize that this is something similar to what happens for computability. In computability, the class of computable functions is stable by many properties, so it's very stable. And here you have exactly the same. So the class of generated functions is very wide. Of course, this doesn't include all functions, because first, if the function that you want to draw is not derivable, then of course you could not draw it that way. And you could say that the generated function must be analytic. So analytic means equal to its Taylor expansion in any point. So one question we could ask, and that were the purpose of a remark from Claude Shannon, is, do we know some example of functions that would not be programmable, not generable using this machine? Yes. The two famous counterexamples are Euler's gamma function and the zeta function from Riemann. So yes, we know counterexample, but in short, if you avoid these two examples, most common function can be programmed. So it has very nice closure property. And just to mention, the set of constants, so things that you could observe at time one, is a field, and it's an open question to characterize this field and relate this field to the GNU or the field. Okay, so if you are a mathematician like Claude Shannon and others, actually Claude Shannon was not a mathematician but an engineer, but okay, anyway, if you are a mathematician, okay, we know some property. We know example of function that could not be generated, but okay, let's be discuss this from a computability point of view and be a little bit more realistic about what can be programmed or not. So I told you that there were two examples, zeta, gamma, two examples of functions that could not be generated. Actually, if you want something that is impossible to generate, it's quite easier to take a function which has no derivative somewhere. And of course, you will have a trouble to generate the function, to draw it. So a simple, very simple example is the absolute value, which has no derivative in 0. But let's be honest and say, how would you draw something like the absolute value on my oscilloscope? You will do exactly what the engineers of that time did. So not draw absolute value, but draw something close. So something close could be, think you, so you go to example of function which could be close. So you could take something like the hyperbolic cosinus, which has a shape which looks like absolute value, but okay. Another example is take tangent, hyperbolic tangent x times x, which is drawn here using GNU plot. So it's not exactly this shape of absolute value, but not far actually. And I wrote here the equation just to convince you that it could be drawn on my oscilloscope by just programming this polynomial ODE. Okay, you could say this is not the same, but if you want to do better, just put a 2 here, it would be better. And if you put a 100, it would be even better. And I think that at least from with GNU plot on my screen, I don't see any difference from absolute value and this function. And actually, if you give me any mu, a precision mu, I could take some constant k big enough so that I would be sure that the error stay of order exponential minus mu to the absolute value. Okay, and okay, so okay, you could think about that and realize that the problem is if I want to draw absolute value at exponential minus mu, then I need to plug in the initial condition exponential of mu, which you may ask, how do I feed this to my machine? So answer 1, you can draw exponential, so you could get exponential mu and then compose. But just to make the feeling on the way this machine work and are amazing. Okay, so first, okay, just a remark. I need to change, I'm going to change the concept of computations that was proposed by Claude Shannon, motivated by the fact that he wanted to draw a curve on the output table, by a more modern concept closer to what is used for Turing machine. So the Shannon concept was the concept of generation used up to now. So the fact that I could draw the curve on my oscilloscope or output table. And I go to the way we consider computation in 2021. So you give the input x, you give mu as input, you let the machine compute. At the moment you stop it and you read the value. So we say that some function is computed if there is some time depending on the input x and mu, so that if you stop it, you get some approximation of the function. So from that more modern concept, the absolute value could be computed. And I told you, so one trick to do it is clear. Given mu, you compute exponential mu, and then you compute tangent of exponential mu x times x by using the previous equation. But just to observe that we are in a world which is amazing, because this reasoning was a discrete time reasoning. You compute, you do step 1 and then step 2. You are in a context where the time is continuous, so you could do both continuously. Actually, you could compute simultaneously exponential minus mu and this. So you are in a world where you could do several steps in parallel. Analog programming is parallel by nature somehow. Okay. So the point is that if you take this notion of computation, so not real-time computation, but this more modern notion of computation, the absolute value can be computed. And actually the famous two counterexamples, gamma and zeta, can be computed. This was proved by Daniel Grassa in 2004. And after this result of Daniel Grassa, so proving that this famous counterexample could be actually computed by a GPAC, we got to the question, can we prove this model to be universal in the sense of Turing machine? And the answer is yes. Actually, every function that you can compute using a Turing machine can be computed by a GPAC, and conversely. So the model is universal. So, okay, so this is one more new model satisfying the Church-Turing thesis. So it's a Turing universal model. But okay, realize what we are stating. We are stating, if you think about this statement, we are stating that I could define what is a computable function using only ordinary differential equation, polynomial ordinary differential equation. So the notion of computable function can be defined using polynomial ordinary differential equation only. And this fact was quite unexpected. There is no need to talk about Turing machine or equivalent concept to define computable function. If you want something formal, this is this theorem, a function. So here I'm considering functions over the real. I say that a function is computable by a Turing machine if and only if you could build some polynomial ordinary differential equation so that if you feed x and mu, x is the value, mu is the precision, at time 0 to the machine, you let the machine evolve, you stop it at time 1, what you will get on some components, say component number 3, is the value of f with precision exponential minus mu. So this is the formal theorem that we get. I just wrote it. So this is what we obtained something like 10 years ago, and then we went to understand. It was like the obsession, or it took me all these years trying to understand how these models compare to classical models, but not only at the computability level, but also complexity level. I mean, we got the fact that you can simulate any Turing machine using this GPAC or differential analyzer. But could you solve problem faster? I mean, could this machine be used to solve problem faster than usual machine like Turing machine? So can we talk about the time complexity for continuous system? And it's not an easy task. It's because there were several attempts to go to a time complexity for continuous system. Where is the problem? The problem has to do with measuring time when the time is continuous. So of course, you would like to, it's quite natural to say that the time is given by the time variable. But the point is that the variable t is quite arbitrary in the sense that if, suppose I have a machine computing some function, then I can always speed up the machine. So instead of computing y, the trick is that I could compute y of exponential t. So I'm using an exponential speedup. And observe that this new equation can still be programmed and plugged. So if it took me time 1 to do something, then now it computes exponentially faster. So time can be contracted. And of course, if I did it once, I could do it twice. So I could do an exponential of exponential speedup, and actually I could even use tangent or arctangent, I never remember, but even contract the whole infinite line into a finite time. So if you take a measure to be the time, you get that your notion of complexity is not robust. And what we did, so it was the main result of the PhD of Amaury Pouly, was to realize that there is a way to measure complexity in for this model, which is to measure complexity by the length of the curve. So in French, l'abscisse curviligne, in English, or I would say Latin, curvilinear abscissa, which is quite very nice idea and simple idea, which is that you measure the time by the length of the curve. So one reason why this is natural is because if you heard about abscisse curviligne, you should know that one of the big advantages of this notion is that it is invariant by reparametrization. So when I did my transformations above to speed up, this would be some invariant. So this is a nice and natural idea. What was less natural was to prove that it works. And yes, indeed, this is a robust measure of the complexity. Any polynomial time computable function, so by a Turing machine, can be computed by a JPAC using a trajectory of polynomial length and conversely. And we get exactly the same surprising fact. You can define what a polynomial computable function is using only polynomial ordinary differential equation. So there is no need to talk of Turing machine or equivalent concept to define polynomial time computable functions. So let's do it here. So this is quite similar to the previous slide. You say that a function is computable in polynomial time if and only if given x and the precision mu, if there is some polynomial ordinary differential equation, so that given x and mu, it will evolve. And if you stop the trajectory after some polynomial length, then you get f of x at the precision mu. So in short, length is a measure of complexity for polynomial ordinary differential equations. And if you don't like functions over the reals and you want to compute over words, it could be adapted and so on. Okay. Anyway, what I'm going to show you in the remaining minutes is some application of these results. So the idea is now that what we got is that we know how to program using ordinary differential equation. If you realize that in applied science, universal ordinary differential equation is a kind of universal language. I mean, many stuff can be described using ordinary differential equation. So if you know how to program using ordinary differential equation, then it helps you to solve various problems in various domains. And let me mention 3 examples of problems that we solve. So maybe I will focus on the first one only about bioinformatics. So computation using proteins, and just mention 2 others. So the 2 others are we prove the existence of a universal ordinary differential equation. So an equation about a fixed ordinary differential equation able to approximate over all R any function. And we also got to revisit classical computation theory using this tool. Okay, just a few words on this bioinformatic approach. So the motivation is to go to computations by cells in biology and observe that in nature, cells compute. They process signals, they regulate the metabolism, they take divisions, differential migrations. And if you want to describe a system, you could go to naturally to an ordinary differential equation. So here I'm drawing something that I don't really understand, but this is taken from a paper where you see what is the so-called Cons map of the mammalian cell cycle. Just to say, this is a graphical language used in biology to describe big ordinary differential equation. Here, if I remember well, there are 732 variables described here by this graphical language. Okay, so ordinary differential equations do appear in biology. And just to say that actually, if you want to describe a biological system, there are various levels of abstractions according to the level of details you want to model. So it could be the so-called Boolean semantics, where you only talk about the absence or presence of something. You could use the so-called Petri net semantics. You could use stochastic models. You could go chemical master equation models. And we focus here on what is called the differential semantics. So we model the evolutions of, it will be proteins, using ordinary differential equations. So, okay, it's possible to relate all these semantics, and I mentioned here some of the results obtained by François Fage, Sylvain Soliman, about the Galois connection between some of these semantics. But one question that was open was, is the differential semantics for kinetics for proteins Turing complete? There were some partial results about Turing completeness, but just a warning, what we would expect to be called Turing completeness in computability theory is called in this field strong Turing completeness. And you have several results of weak Turing completeness that I will not discuss, but it's non-uniform complexity actually. So the question about whether it's Turing complete for the differential semantic was open, and here is a slide explicitly mentioning this problem. There were several attempts of trying to play with the hypothesis to go as far as possible to discuss this question. So using our technology, we proved that yes, it is Turing complete. Using proteins is sufficient to restrict to binary reaction with a mass action law kinetics. And we prove that it's Turing complete. So what we proved technically was that any polynomial ordinary differential equation can be encoded in a chemically feasible positive systems of double dimension. So in short, elementary biochemical reaction using a finite universe of molecules, proteins, is Turing complete for the differential semantics. So it's computability, and we even go to complexity and proved that the complexity is preserved. So the length of the curve is preserved. If it is polynomial in one model, then it is polynomial in the other. So we got the prix du journal La Recherche and the best paper award for this result and solving this problem. So just to mention how we do that, actually, so we use the fact that we know how to program using polynomial ordinary differential equation. But then we want to go to chemical kinetic reactions. So what are the problems to be solved? There are two of them. First, that we want to encode data by concentration, and the concentration is always positive, while our variable could be negative. So we have to do a trick, and the trick is basically to encode values, but the difference between two positive values. And the second problem was to go to binary reaction with mass action law kinetics. And what we did was to introduce variables so that we could transform a polynomial of arbitrary degree into a degree 2 polynomial so that this is true. Okay. Anyway, I do not want to say more about the various applications and just mention this existence of universal ordinary differential equation that solve a problem from Rubel. So still using this idea of programming with ordinary differential equation. And I want to conclude by stating that my take-home message of many of my talks, including this one, is that there is a strong relation between Turing machines and polynomial ordinary differential equation. And the other message is that programming with ordinary differential equation is simple and fun and an unexpected way to program. Okay. And another message is that many concepts from computer science can be defined using polynomial ordinary differential equation. So I stop here. Thank you.
Thank you, Olivier. Are there any questions from the audience? Yes. Go ahead.
Bonjour, merci beaucoup pour l'exposé, c'était vraiment super intéressant. Je suis arrivé un petit peu en retard, j'ai raté le début et je ne suis pas très familier avec les équations différentielles, alors j'espère que je ne vais pas poser des questions trop stupides, mais j'en ai deux, trois. La première, c'est quand tu as parlé de... Ah, sorry, maybe I should speak English, no?
As you wish, I understand French. But...
Yes, so yes, maybe I will continue in English for maybe some people not understanding French. So at some point you talked about the 21st century way of defining computation, like not with a fixed time, but at some point we should get an answer. And when you said it, you say that there should exist some time where we get the output, but in every drawing, it was like it should converge to the output. So can you precise a bit what is the definition of the result of the computation?
Okay, so actually, I wanted to avoid technical details and not go to too technical issues. So okay, but in short, in the slides, I discussed the computability of functions over the reals, because this is the most natural way to talk about ordinary differential equation, but maybe. So in that sense, you give x, so x is the input of the function that you want to compute. You give mu, the precision, and when you stop the machine, you read some value in some component, and this value will be f of x with error at most exponential minus mu. This is the thing.
Okay, and how do you know when to stop the machine?
So then the thing is that one way could be to say that the machine is able to produce on some other components a kind of signal that tells you when to stop the machine.
Okay.
But okay, this is one way to answer. No, the point is that we simulate Turing machine using ordinary differential equation. So somehow you must understand that if you ask the same questions about Turing machine, then I would have to say that many conventions are possible and that could say that they stop that way or the other way with a blank tape and so on and so on and so on. You could do the same. I mean, it's not important. So it's really tricky when discussing this with ordinary differential equation, but at the end, any way to signal that the computation is indeed that looks similar to something that you would do with a Turing machine is working.
Okay.
Yes.
Okay.
So it's a very robust notion of computation.
Okay, nice. And about the simulation of Turing machine, I'm curious about how you encode some Turing machine configuration as a set of real variables, and can you say that the simulation is like step by step? I mean, when you develop the differential equation, it's like really we can see the steps of the Turing machine, or is it different?
Yes, it is step-by-step simulation, and we mostly encode the configuration of a Turing machine. So the trick is to encode the tape in the digits from real numbers.
Okay. Sounds like yes, intuitive idea. Okay.
So the point is that we have to do with. So this is the idea. The trick. The overall trick is that we have to do with errors. We want to do that, but we have to correct errors, and we correct errors in almost all the stuff and the equation.
Okay. So that answers another question that I had, so I continue to ask questions, but if I'm too long, other people wanting to ask questions, just stop me. And so at another point, you say that you can speed up when talking about the complexity. So you say that the first difficulty is that you can speed up the computation of partial differential equations. And after you say that you can even shrink an infinite time into something finite. So with this you can solve like halting problems of things, or what?
Yes.
Okay.
No. Okay. You have to understand something. When we go from a machine to a mathematical of the machine, we go to an abstraction. So if you have some differential analyzer, I have one behind me. Go to zoom. So I'm drawing here the Lorentz attractor. Suppose I want to slow down or speed up the machine, the attractor. It's quite easy. I just turn my potentiometer, and then it's slowed down. Okay.
Is it possible that you stop sharing the screen so that we can see the video bigger?
Do you? Okay. I'm trying to do it. It's quite tricky to play with. So it's the same but slower. So it's the same shape. If I turn the potentiometer in the other direction, it would go faster. Okay.
Okay.
So this is the machine. Now, if I go to the mathematical abstractions, the point is that I'm playing with the constant. Now, what I told you is that at the mathematical abstraction level, yes, I could solve some the halting problem of a Turing machine in finite time. It could be programmed, at least in theory. Then I'm not claiming this is possible to go to the concrete machine, because
yes.
of course, then we go to questions about physics. My talk was about mathematical abstraction and mathematics. And if you want to solve the halting problem in a finite time, Then you have to go to concrete numerical problems when going to physics. But yes, at the mathematical level of abstraction, yes, I can solve the writing problem. And somehow this was the key motivation for me of this going to complexity issue. Could I prove that it's not possible to solve the halting problem using a machine? And so at the end, the conclusion is it's not possible unless I accept that the length of the trajectory could explode. Yes, so the length. So if I consider that the length of trajectory is something that should not explode in practice, we have a complexity theory.
Okay, okay, yes, that's quite clear. Okay, thank you. And so maybe I have a last question, but it's more personal and about curiosity. And how much does it cost a JPAG computer?
Okay.
Or the way you build it yourself. I mean, it's not a hands-on thing you can buy.
Okay, so this is the part related to publicity. So two things I have to tell you. I do have here some differential analyzer. The one I got here is sold by Analog Paradigm company, which is a German company. And this one, so it's a modular one, so you can buy various components in the machine. But I would say this one is about the same price as the Mac I'm using to do this presentation. So it's something like, I don't remember exactly the price, but it was something between 1,000 to 3,000.
Yes, okay, okay.
Including everything. I mean, the point is that if you buy a Mac, then you have to buy all the... So, and of course, it's also because there's only a prototype and so on. But I have also to sell you here, this is a Turing machine, a prototype. So if you want to play with this one, it's really cheaper, but okay. So my office is full of stuff.
Things that compute mostly.
You can buy this, and so this company, Analog Paradigm, is selling some machines, and it was funded by Bernd Pullman, who is a fan of old machines. And we are trying to make some new prototypes more efficient, and he wrote some books about the history of computing and so on. But okay, yes, but not so expensive, except that, of course, it's not really at the moment interface with the computer. So yes.
Okay. Okay. Thank you very much, and thank you again for this great talk. Thank you.
Thank you, Dean. Are there any other questions?
Maybe one question. Is there a notion of completeness in the world of differential equation?
Let me, yes and no. What is completeness for you?
In the sense of NP completeness, or if you have
yes, so somehow yes. Yes, because we are able to relate our problem to the classical problem. So somehow, when we say that we know how to talk about complexity theory for ordinary differential equation, one way to state that would be that solving some ordinary differential equation is P complete. So yes, but no, The other thing you should understand is that when, so the example you gave is NP completeness. So NP is for non-determinism, and currently I do not know what would be. So, I mean, we are able to talk about complexity, but not about space complexity, not about non-determinism, and so on. So somehow the current understanding of the theory is quite weak. So we have no notion of NP completeness, except by trying to put the classical notions. I mean, unless if we try to cheat and express the fact that an NP problem exists something over P. So there is no simple notion of completeness, but we could get one, and it makes sense, yes.
But maybe you have a notion of reduction, and that takes into account the resources in time and space, I think.
So yes, we do. Yes, we do. Mm-hmm. So from a positive side, yes, we do have this. From a negative side, when we go to simulations of a Turing machine by ordinary differential equation, somehow we often go to describe the most awful polynomial equation you could imagine. I mean, so it goes also to completeness. I mean, the one able to simulating a universal Turing machine is expected to be very hard to be simulated because it could simulate everything.
Thank you very much.
If there are no other questions, we can thank you again, Olivier, for this talk. And let's update for the next one in May. You will find the record of this talk on the webpage of the seminar. So thank you again, Olivier. You can also clap. But,
Merci de cette invitation et bonjour à tous. Bonne journée à tous.
All right.